So in this lab, we will use analog to digital converter. So our processor, as many processors, has analog to digital converter. So let's check it out from the peripheral point of view. We will need reference manual. We will also need user's guide for this kit so that we know to which pin some analog signal is connected. Let's say user's guide here, and maybe also datasheet. Datasheet is here and this. Okay, so analog to digital converters are pretty simple. You select a reference voltage, analog to digital converter right here. So you select, positive input is usually some pin on the microcontroller. Negative input in the simplest form is just ground. If you want, you can also use this analog to digital converter in differential mode, where you measure voltage between two pins. But in our case, we will just measure it against the ground. And then you also select the reference voltage. You want the signal to be from 0 to the reference voltage and not going outside of these bounds. But generally, that's how this analog to digital converter works. And it gives a number from 0 to maximum value, which is proportional to the signal with respect to the voltage reference. For example, you select 2.45 volt reference, your signal is 2 volts, the output will be 80%, which will result to some number which is 80% of the full scale. So pretty simple. And on our development kits, we have one analog signal source, and it is right here, light sensor. Somewhere on your board, there is a light sensor. So on my board, it's right here. It also says light sense. So this is a very simple transistor, photo transistor. Let's check out its circuit. It is also in this user guide, and it is located right here. So this is a very good example of how to connect a sensor. So basically, there's a resistor and the transistor, and basically in the simplest form, it works like a switch. So when the light shines on this transistor, it conducts electricity, is like a short circuit, and this resistor has full voltage on it. So it will be the maximum voltage. And when you remove the light, this transistor stops conducting, and this resistor pulls the input down to ground. In our case, so to use this circuit, we need to set port D pin 6 high, so that this is also called light excite, so that we turn on this circuit, and then we measure through port C pin 6. And after we have finished the measurement, we switch off the light excite so that this circuit doesn't consume or waste electricity, because if we leave it switched on, then this circuit conducts electricity all the time when the light source is present, and we will have some high leakage current, and the battery will be drained quickly. So this is very common that you turn on some circuit, you do the measurement, and then you switch the circuit off. Let's try to do all of this. So what we will do now is we will create a new library, which we will call analog. And in that library, we'll initialize this thing and do the measurements, and manage everything and make some simple API. Except one thing. Port C is connected to analog comparator, so we could use this circuit as a switch with some threshold, but we want to use it in analog to digital mode. This is why on your development kits, you have a small jumper between pins number 7. Oh, and there's no connection. And between port C, pin 6. So in the newer version, it looks like it's a no connection pin, which is not good. On older development kits, there's port D7 and port C6, and they are connected together. I don't know if you have it, but there's a jumper which you need to leave on between port D7 and port C6. I'll try to find an older datasheet. STK 3600, I guess it was the name. User's guide. Yeah, this is an older version. Now I'm starting to wonder if you will be able to do this lab if you have a newer version development kit. But if you have an older version, you should be able to do it. Let's just find the pinout. Port C6, 1 second. Okay, yeah. So on older versions, port D7 is pin on the bottom row, the second pin, and port C6 is bottom row, third pin. So on port C6, we have this output of light sensor connected, but port C6 does not have analog to digital converter capability. Only port D, pins 0 to 7, have a internal connection to analog to digital converter. So we have a short circuit jumper between port C6 and port D7, so that the output of light sensor is connected to port D7 of analog to digital converter, and we can sample the signal. So on your development kits, please leave this jumper on. Do not remove it. It's between these two pins, and let's leave it there. And now let's try to write some code with which we are able to do the measurements. So in our development kits, in the source folder, in our Simplicity Studio project, let's create a new library. So new header file, I will name it analog.h, and also new source file, analog.c. And in analog.c, I write hashtag include analog.h. And in analog.h, let's just estimate what peripherals we will need. First of all, to use analog to digital converter, we need to add mlib analog to digital library. So I browse files here, and here I find analog to digital converter library emadc.c, Studio SDK location. So emadc.c is here. So I write hashtag include emadc.h. The header files are automatically included in the project by Simplicity Studio. We just need to drag and drop the C files. Next, to use analog to digital converter, obviously, as previously, we need to turn it on using clock management unit. So in analog.h header file, we also need to hashtag include em_cmu.h clock management unit, and also GPIO unit, because to turn on this circuit, we need to set port D6 pin high. Hashtag include emgpio.h. Okay, so these are the things. And of course, as for all libraries, we have some initialization function, void analog_init, void. With this thing, we will turn on ADC and, maybe something else. So in this analog.c, we write the implementation. So we want to use analog to digital converter. It also has documentation in mlib, in ADC. And here are some initialization informations and usages of functions. So what we are going to do is we are going to initialize analog to digital converter with ADC init typedef. And also, if we want to measure something, we need to initialize a channel using ADC in its single typedef. It's for channel initialization. So first of all, I need to turn on analog to digital converters clock. So I type clock management unit underscore clock enable, and the clock name is CMU clock underscore analog to digital converter number 0, because some chips have multiple analog to digital converters for synchronous operation and multi-channel sampling. So it has some number, but in our case, we only have analog to digital converter 0. Save all. And let's see. Next thing that we need to do is initialize our excitation port and excitation pin. So in this user guide, we need to check out which pin is connected to light sensor and initialize them accordingly. So here, light excite is port D6. So the correct way to do it is in the C file, write hashtag define light excite port GPIO port D, hashtag define light excite pin number 6. And here for initialization code, I will write GPIO pin mode set. Port is light excite port. Pin is light excite pin. And mode, GPIO mode, is push pull. So we set it high or low. And level initially will be 0. It means off, low level. So if you have this pin to ground, then there's no current flowing from ground to ground. So this circuit is off. Okay, next we need to initialize our analog to digital converter. So I will use this analog to digital converter init typedef structure. My ADC settings equals to, and in curly braces, I can, implement something. And again, control clicked on ADC init typedef brings me to the definition of the structure with all of its fields or properties. And also there's an example default settings that I just copy and paste into my code. So analog to digital init typedef my ADC settings. So first thing is analog to digital converter over sampling rate select. So this analog to digital converter is capable of sampling multiple samples and just adding them together. This way you get a better noise resistance because it averages several samples automatically. Initially, we will not use it yet. Next is there's also a built-in low-pass filter. It's not very good filter, but it's better than nothing. So you can use it. You can use filter RC, or you can only use the built-in filter decoupling capacitor, which is small, but sometimes it's good to have it. Then there's the swarm up methods. It can be, fast bang up, which means that it will be less precise, or keep reference warm, which means it will use more current, but it will stay warm all the time. But we will use normal warm up so that when you need to sample, it warms up the ADC, then it does the sampling, and then it switches it off. It takes a little bit more time, but it it works the best probably. And then reference clock will be calculated automatically and tailgate not used. So basically we just leave the default settings and we send these settings to ADC using ADC underscore init And the first argument is ADC 0. And the second is address of ampersand shift 7, address of my ADC settings. Okay, so this initializes the analog to digital converter. Then we want to initialize a channel. We want to say that we want to sample from port D7 because we have this jumper on that port. These are two connected. Port C6 is the physical connection of the sensor, port C6, but unfortunately it doesn't have ADC connectivity built in because only port D pins from 0 to 7 can be used for this purpose. So we had to put external connector. So to initialize analog to digital converters channel, we need to use analog to digital converter init single type def. So ADC init single type def. And I'll name this variable my channel settings equal to, and curly braces open and close. And again, I control clicked on this definition, and it also offers me an example structure with some default settings. So let's check out. When I initialize a channel, I can, well, this PRS is not something that we use, so we don't change that. What I can do is I can change how long the input is being sampled before starting to convert it. You know, if we have a source with very high internal resistance, then we need to acquire the signal for longer to wait for this analog to digital input sampling capacitor to charge up to the level of the signal. And if the internal resistance is very small for the signal source, then we can set it smaller. So right now I'll leave it as acquisition time 1. Then we select the reference. Let's check out. In this case, the analog signal can be from power supply level to ground level. Power supply, when this transistor is fully open and is short circuit, then this pin is basically connected to power supply. And when it's off, it is pulled down to ground through this 22K resistor. So the reference that we should use should be power supply voltage level. So instead of 1 volt 0.25, I need to use ADC ref VDD. So here we have to change it. Then we leave 12-bit resolution. We have possibilities 6 bits, 8 bits. 6 bits will be fastest, but it will be less precise. 12 bits and also oversampling, where it adds multiple 12-bit results together and you get 13 or 14 or 16 or 15 bits as a sum of multiple samples. We will not use it yet. And then we select which input channel we want to use. And in this case, the channel number is the same as port pin number. So we use port D7. So the channel number is 7. Oops. So we have analog to digital converter, single input channel 7. So single-ended is the result. It's not differential. We don't use PRS. We don't want to have it left adjusted. And we don't want to do some scanning. So the rest of this stays the same. So we changed reference and channel number. And we initialize analog to digital converter channel. We're using ADC init single, and we name ADC 0 and address of my channel settings. Okay, so far so good. And now we want to sample the signal. So we basically want to ask what is the voltage on this light sense pin. And then we determine if it's high, it means that there's a lot of light. And if it's low, then it means that there's no light. So let's create a a function which will basically just return us the analog to digital converter value. So unsigned 32-bit integer. The analog to digital converter is only 12 bits, but let's just put the value in 32-bit register for now. So we will create a function which returns unsigned 32-bit integer. We will call it analog get light level, and it has no arguments, so void. Okay, so and this function, we will write an implementation in our light in our analog.c file. And basically what this thing does is we will just ask the analog to digital converter to sample the signal at the input port D7 and just return it. And that's it. So we do it in the following way. Analog to digital converter starts a conversion. Let's see. I'll check out the code from the previous semester so I don't mess up. And it also needs to wait for the conversion to finish. So analog. Okay, so let's check out and close this project. Okay, so the code to start analog to digital conversion is done by calling ADC start with argument analog to digital converter 0. And then what kind of command we are going to give to it. ADC start the command name is analog to digital converter start single. So with this we say, just do one single conversion, just sample the channel 7 and return. And then it only initializes the conversion. Now we need to wait for this function to complete. And it's done in the following way. We need to wait until analog to digital converter 0 status register gets a single data valid mask bit set. And it's done with this line. While is not set, analog to digital converter status register bit single data valid, we just wait. We just wait for analog to digital converter to complete. And then we just return analog to digital converter data single get analog to digital converter 0. So and one thing that we need to remember before we do the sampling, we need to set this pin high, and after we finish the sampling, we set this pin low. Initially, let's just leave it high all the time. So I changed this GPIO pin mode set light excite port light excite pin high so that it consumes energy all the time, so we can check out with how much electricity it's consuming. So let's set it high for now. And this is how the analog.c file looks like. And so I save it, this analog.h, save, and in the main code, let's write it this way. So instead of printing all the time hello world, let's print, light level equals to %u and new line in the end. So in here I put analog get light level. So with this thing, I want to print out analog light level. So it will perform this analog get light level and print out its value and put a new line at the end. And it will do it once every second. So it prints out this text, then waits for it to finish printing out and then goes to sleep. So this will be our sample experimental text and code, and I'll compile it. It compiled without mistakes, flash size 22.7 kilobytes. I will flash it and let's check out what the output is. Okay, do we get some information here? Looks like it's not working. Oh yeah, we need to initialize the analog to digital converter. I keep forgetting it. So first of all, hashtag include, double quotes. You see our code asks for analog to digital converter to sample a signal, but since it's not switched on and it's not enabled, this thing just hangs in this place. So we need to first include this analog.h library in our project. And also, of course, we need to initialize analog to digital converter using analog init. And now we build this code, flash it again. And here we have some output. Okay, so it says light level is 2304. I now put a hand over the light sensor, which is right here, and it shows a small value. You see, it says 9, 11. I remove the finger, it shows a bigger number. Now I will take my cell phone's torchlight, I'll shine it, directly onto this sensor, and now it says, 1000, 1400, bigger number. And if again I put the finger on the sensor, it's dark for the sensor and it shows a smaller value. So the code seems to be working. Now I put it under my desk lamp and it shows 2000. So this code is working. So you can try to compile it and check out if it works for you as well. Okay, now it shows you light level. Let's try now to let's check out the energy consumption. Okay, let's check out how much electricity this circuit consumes. So I start energy capture. Okay, I think while the energy capture is active, it uses the same USB connection. So it pauses the UART because it cannot simultaneously sample the signal and also use UART. So let's zoom in and pause. And as you can see, when the microcontroller is sleeping, instead of 1 microamp, 1.5, it uses almost 100 microamps, okay? And when the LED is on, yeah, it uses more microamps. We expect that, but this circuit, if we leave it turned on, it consumes approximately almost 100 microamps, right? So the LEDs use 500, and here's 594, and here it's 98. So basically, this voltage divider keeps consuming something like 95 to 100 microamps, which is, quite a lot. It's not such a small number. If I put it in the darkness, yeah, it consumes less because this transistor is off, so it doesn't allow electricity to pass through. So when it's dark, this circuit consumes very small energy. But if it's bright, then this transistor is on, it passes the electricity through, and it consumes quite a lot energy. Okay, so as I mentioned before, what we can do is we can switch this circuit off by setting light excite low and keeping it low all the time, keeping it off all the time. And then when we want to sample, we set it high and then we sample it. So let's check out. I will end this session in sampling of energy and change the code in the following way. When we call analog get light level, we want to first turn on the circuit, GPIO pin pin out set. With this, we set light excite port, light excite pin high, so that we turn on this circuit. And then we do the sampling, and before we return, we turn off the circuit. So GPIO pin out clear. Light excite port, light excite pin. Okay, now, and also when I initialize this port, I want it to be off. Okay, so I switch it on before sampling, I switch it off after sampling. Let's see the energy consumption. So I compile this code, I flash it to the device. Okay, it works. Let's look at the energy profiler. Okay. And as you can see, the energy consumption is small. It doesn't matter, I put the sensor in the darkness or I put it in bright light. You know, energy consumption didn't really change much. It increased because I touched it with the finger and there's some leakage current from my finger to ground. So this is why there might be some small energy changes. But if I take this cell phone with bright light and shine it there, energy consumption doesn't change. And how much is the energy consumption? Let's see. So the microcontroller, while it sleeps, it consumes 1.83 microamps, you know, slightly more than before, but it's still very small, you know, it's 1 and something microamps. And when LED is on, then back to 498, almost 500 microamps. So we reduced the energy consumption significantly. So, you know, that's good. But now let's check out what the output of this sensor is again. It says 3,600 and something. I put a finger on the sensor and it still shows me a big number. And I remove the finger and it still shows a big number. So even though we, you know, we reduce the energy consumption, suddenly our application isn't working right. You see, previously, when the sensor was on all the time, when I put the finger in front of it, it showed something like 9, light level was 9 or 7, something like that, some small leakage current. And when I removed the finger, it showed something like 2,000. Now it shows 3,800 almost all the time. So what is happening here? Maybe what happens is we open, you know, we set this light excite level high, but the current hasn't really started to flow through this circuit when we sample it, and this is why we get some results. However, if it was the case, then when we set the spin high, then and we sample too early, then we should get a very low result, not very high result. And the thing here that happens is when we turn on this transistor, it has some capacitance. And here the circuit that we actually get is power source, capacitance, resistance, and from the midpoint we make a measurement. So when we set it high, this capacitance of PNP transistors, NPN transistors, collector to emitter, the capacitance only is charging up. So there's something like short circuit from AC perspective, and all the voltage is on this resistor. So what we have here is that the circuit is in transition while we measure it. So the correct solution would be the following. We set the pin high, and then we wait for some time for this circuit to fully start working, for all the capacitances to charge up, for this transistor to start conducting in its normal mode, and only then we make this sampling. So we can do it in one of two ways. First, we can increase the acquisition time. We are sampling too early. We need to set higher acquisition time. To find out the acquisition time, there are several things that we can do. Basically, what we can do is we can sample very quickly the signal and check out, at what time it reaches some value. So let's write a simple loop for I equals 0, I smaller than, 100, for example, I plus plus. And let's create some buffer. With 100 elements, and let's sample analog get light level into this buffer. So buffer with index I equals 2 analog get light level. So we quickly sample 100 times this analog signal with one little change. We will set the level of the excitation pin high initially, and then leave it high. So what we need to do is basically turn on the excitation part and comment it out here. Then close it after sampling and comment it out here. And in our main code, these things are undefined because they are defined in analog C. So in this small test program, I will write it with these bad names. So it's pin 7, 6, and 6. So with this code, what we basically do is we create a buffer with 100 elements, which is initially empty. Then we set port D6 high, this excitation signal high. Then we quickly sample 100 times the analog signal. And only then we switch off this excite pin. And then we print out the signal level. And let's just see if we see some transitioning pattern, which tells us what exactly happens to analog signal. Why do we have these high values at the output? So for I equals 0, I smaller than 100, I plus plus, print f. And let's just print out these values, percentage sign, U, new line, and buffer I. So let's try out this code. And let's see what we will get at the output. So as you can see, it is initially 3,800, but then these are 100 samples. Then as the time goes by, on each of the next samples, the value gets smaller and smaller and smaller. Let's see it in Excel. And let's draw a graph here. These are probably 100 samples. Yeah, as you can see, it's 100 samples. And let's plot them on graph. This is how electronics engineers do it. We sample it to termite and then put in Excel and draw a graph. And as you can see, when we open this, when we excite this circuit initially, the voltage is high, and then it takes some 100, I don't know, microseconds or something like that, and then it normalizes to some level. Now let's do the same thing with light sensor being dark. Okay. So it was here, it will be even more visible. So I copy it here, I paste it there. As you can see, what I'm saying is, true. When we turn on this circuit, when we set it high, it takes 100 samples for this thing to level out, to reach its normal situation. And actually, maybe we would actually need another 100 sample times for this thing to normalize. So basically, what we have to do is, when we set this excitation pin high, we need to wait for some time for this circuit to normalize, and only then we can sample. So how can we know how long time we need? Well, from this Excel, we can see that we need at least 100 sample time. How much is each sample? This analog to digital converter works at 7 megahertz. It takes the CPU's frequency and divides it by 2, so it's 7,000. So it's 7 million hertz. But each sample takes 13 these clocks to finish, because for successive approximation register analog to digital converter, each bit is 1 tick, and there is plus 1 tick for acquisition. So divided by 13. And then we have some extra code, which is, but that's probably pretty fast. It's acquisition and buffer increments. So, it's a little bit addition. So we calculate the period of each sample. So each sample takes approximately 2 microseconds, and then we multiply it by 100. And we see that we need approximately 200 to 400 microseconds for this circuit to normalize. So the correct thing to do would be, in this analog get light level, to set the pin high and then delay some time. I don't know how much, maybe 1,000 microseconds, maybe 100 microseconds, but some delay. Then we sample and then we switch it off. So what we can do is we can just copy this delay 1 second function from the main code and paste it to analog.c, and we will rename it from delay 1 second to simply delay excitation, and put this function after we set the pin high for it to delay some time. Right now it is set to, I don't know, something like 7 seconds. Let's see. And I will show you a trick how we can quickly find the value of this excitation number, so that we get some correct delay before we sample this unstable analog signal. So analog get like level, delay excitation. Let's set this value, so we calculated that we need this value to be approximately 2 milliseconds. Okay, so we remember that each of these cycles took something like 7 instructions. So 14 megahertz divided by 7 is approximately 2 million ticks per second. And we need something like 2 milliseconds for this thing to happen. So we divide it with, I guess, 500. And we get that we need this counter to count from 0 to 4,000. And then we can expect approximately 2 milliseconds of an active delay. So GPIO, pin outset, light excite port, light excite pin, delay excitation, it's approximately 2 milliseconds right now. Start single, wait for it to complete, and then switch off the pin and return. And in the main code, I will, comment, or rather delete this test code. I will comment it out so that you can also write it down and try if it works for you as well. So this code just quickly samples 100 samples and then displays them. Or better, I just delete it so you're not confused. But now analog get light level, sets the pin high, waits for some time, samples, and puts the pin low and exits. So now I build this code, I flash it to a device. And let's look at the output. So when I put the finger in front of this sensor, it says 29. Previously, it was something like 9. So it's still a bit too long time, too short time. What I can do is I can double the time from 4,000 to 8,000. And you might say that it's a very big increase, but I can keep a lot of intermediate values this way and actually get the result faster. So now it counts from 0 to 8,000 and only then exits. I put the finger in front. So now it says light level is something like 15, 14. Okay, I think it's still too little. So I double this again from 8,000 to 16,000. I flash it to device, program, and let's look at the output. So when I put the finger in front, it is 11 to 12. It's a little bit closer. But now it's just a question of, the taste. Do I accept 2 or 3 level difference, but it takes 2 times less time for this delay to measure, and I save 2 times more power and battery life? Or is it not acceptable and I want it to be this long, but get a more precise result? Usually in these low energy systems, people rather have the code execute faster and be less precise. So in my case, I just put it back to 8,000. And I know it's a little bit off, but I can deal with it, but I save some energy. And now if I build this code and flash it, I know it's a little bit off, but I can accept it. So now it says 13. I say, well, fine. And now let's also check out the power consumption of this board. Okay, and let's zoom in. So as you can see, when the device sleeps, it consumes 1.78 microamps. when the LED is on, it consumes for 197 microamps. That's fine. And then we zoom in this period. And as we can see, it takes something like 5.7 microseconds for this thing to excite. Then, so by the power consumption, we can understand how long each part of this code takes. So if we look at the main code, basically the printf first calls analog get light level, and only then will it start to output this text. This is how C programming language executes code. If you have a function which depends on another function, then this function is called first. So first, the code goes to analog get light level. In this code, it sets pin high, this excitation pin, then it waits for some time. In this case, we can measure it that it is 5.6 milliseconds. Then it does the analog to digital conversion, which is very fast. And then it switches this voltage divider off, and we can see that the current consumption also went a little bit down. Not by much. So here's 5.25 microamps, and here's 4.15. And then this time is used, this 1.3 milliseconds is used to send out this light level equals 2 and then some number to the termite. And then the device goes to sleep. So here we can, by measuring the current and noticing the current consumption change, we can also measure how long this excitation delay is. And now we see that it takes some 5 microseconds for the signal to stabilize, and it's not great, but that's the price that we have to pay in this case. And it samples, and when it exits, this thing consumes very small energy. And in some applications, maybe you want to use a different light sensor, which works faster, which is maybe smaller, maybe with a lower internal capacitance, or you just want to sample it even less frequently. Okay, so I will now show the code on the screen so you can type it down. And your job is to copy this code, write it in your programming environment, compile it, test out that it works, measure the current consumption, and then upload it in Ortus so I can see that you did this lab. So this is the main code. We added this line and also analog init and include analog.h. We also drag and dropped inside the mlib folder em analog to digital converter library em ADC. Then we also created the analog.h and analog.c library. Here's the content of analog.h. And here's the content of analog.c. Yeah, all the code fits in one page. So you can type it down and test it. And one more thing that we can do. Oh no, we're not going to do it. We will do it in the next lab. Okay, so that's about it for today. And write the code, compile, test, and see if it works.